Our next speaker is Reszela. Zbigniew works as control engineer at ALBA Synchrotron for 9 years. During this time, he was involved in building control systems for beamlines and developing Sardana and Taurus frameworks. In the very last years, he's been involved in the generic continuous scan project for Sardana. He will give us a talk titled Sardana-based continuous scans at ALBA, current status.
Okay, thank you for the introduction. I will give this talk on behalf of all these people listed here that were involved in this project. So there are 4 main parts. At the beginning, I will give you an introduction to the Sardana. Then I will talk to you about the generic scan framework project in Sardana. I will make a quick demo of a continuous scan with Sardana, and at the end, I will iterate over the continuous scans application that we run at ALBA. So let's start. Sardana is a scientific SCADA suite. It is based on Python. It is open source. And its architecture is highly modular, so you could use just part of it for your needs, and is easily extendable with the plugins. It was initially an internal ALBA project, but after its successful application at ALBA and other European synchrotrons, it became the community-driven project. It is based on the client-server architecture and uses Tango as the middleware. So on the client side, we have Taurus user interfaces. Taurus is a framework for creating graphical and command line interfaces. It can interact with different control systems like Tango, EPICS, or any other data sources. So Sardana users may choose between the between SPOC, which is the command line interface based on IPython, and it mimics the spec command syntax. The other choice is to use Taurus widgets or complete graphical user interfaces. And on the server side, we have 2 main elements. The macro server, which is the control environment for running user procedures. We call them macros. So this is Python code. And the developers of macros may choose between numerous features while developing macros. Also, a macro server comes with a set of predefined macros. This includes also scans. Then another element of the server side is the device pool, which unifies the hardware access to the Sardana system, which is basically a repository of the hardware elements. And it is easily to plug in a new hardware to the system via the controller classes, which are also Python code. It defines a set of generic interfaces for the most common beamline or laboratory instruments like motor, movables, or experimental channels. On top of them, it is possible to build more advanced interfaces like virtual or pseudo elements or groups, and also generic widgets. So I will maybe start with the definition of the scan now. So scan is a measurement process that involves the changing of a parameter, usually a movable's position, and acquisition of the experimental channels. The traditional way of executing scan is a step scan, where both operations are executed sequentially. So these blue areas, they represent the data acquisition, and the curve represents the changing parameter, in this case a motor position. And the modern way of executing scans, which are the continuous scans, where both actions are executed simultaneously. So continuous scans, they allow to reduce the natural time overheads of step scans, the ones related to the motion, like the acceleration, deceleration times, or instability times, and also the ones related to the software state transition. So we need in the step scan to determine when the motion ended and the acquisition can start, and vice versa. Also, continuous scans, they require the high precision synchronization, and 2 possibilities exist to synchronize by software. But in this case, the acquisition state transition cannot be, overheads cannot be reduced. And the hardware synchronization, which allows to go to the fastest scans. Also, in continuous scans, in order to achieve the data acquisition while movables are at constant speed, we need to extend the effective motion range on both ends. This exposes the scans on the risk of hitting the limits, and also adds an extra time for handling this displacement, or maybe basically not intuitive to the end user. Also, continuous scans the data acquired corresponds to the time and the position intervals, in contrast to the step scans, where the position is unchanged during the scan. And this has to be taken into account when we want to have reversible scans in one and the other direction, and we need to choose a proper type of the triggering in this case. So the generic continuous scan project in Sardana started in 2013 with the conceptual design that was explained in these proceedings at the ICALEPCS in San Francisco. At the same time, we had 3 ad hoc solutions for the continuous scans at ALBA. However, they lack of generalization. They were oriented to the single type of the synchronization device. The software synchronization was not possible, and also it was restricted only to the scalar experimental channels, so 0-dimensional. Then in 2015, after a set of prototypes we have implemented, we had the complete technical design, was explained in this proceeding, and we had started an interactive development of the framework. The intermediate versions were regularly deployed at ALBA Beamlines. What gave a benefit to the scientists by the intermediate time reductions of the experiment, but also brought an extra difficulties for maintaining different versions at different beamlines. And currently, we have reached a major milestone, which is the integration in the Sardana, the generic scan framework, and we have also upgraded all our setups to the recent version. Now I will make a very quick demo of how to scan with Sardana. So in order to scan with Sardana, first we need to integrate the hardware in the system. So there are 2 possibilities. Either we can reuse an existing controller code that is uploaded in the third-party repository, or we could develop a new plugin to control either a movable, an experimental channel, or a synchronizer. And this is also relatively easy with a Python class and 4 or 5 methods that are necessary to be implemented. The second step is to configure the experiment, so select the experimental channels in the graphical or command line interface way, and optionally configure saving or online plotting. And at the end, you are able to use turnkey scan macros available in the step, continuous, or time mode. Now I will make a quick video demo of a scan in Sardana. We will populate the system from scratch that will involve an ADC channel, one tango attribute that proceeds directly from the tango, and a motor, a single stage stepper motor, and we will use in the continuous scans all the hardware synchronizer. So we will create a Sardana system from scratch and connect to it from the command line interface. So let's start. So we start the Sardana server. Also different possibilities are available with different architectures, but for the simplicity we'll use just a single server. Then we start the Spock command line interface. We could see that it is empty, but we have predefined controller classes in the system that are available in the third-party repository. And in order to avoid the population from the command line, I have created a simple macro that will populate all these elements. And it also creates the Taurus attribute element that will connect to a Tango attribute, but it could also connect to, for example, to EPICS. And we run the macro, and now we could see that all the elements are already populated in the system. So now we will configure the online plotting just to visualize what we scan. We have all the experimental channels in the measurement group, and now we are able to configure the online plot. Different possibilities exist for the online plotting, but since we use the scalar experimental channel, we'll just make a trend for them. Other additional experiment configuration is also possible from this widget. So now we will see a very simple example of a scan. First, we will start with a step scan, where we specify the motor that we want to scan, the start of the scan, the end of the scan, the number of intervals, and the integration time. And we could see like that we are executing a step scan because the motor is accelerating, decelerating for each scan point. With exactly the same configuration, we could execute the continuous scan that we will now proceed to that. In this case, we use the default configuration, which is the software synchronization. We just changed the name of the scan, and we could see that with the same parameter, the experimental channels cannot follow the rhythm of the scan because of this software state transition necessary. So we have two options now, either to enable the interpolation of the data or to add an extra latency time that we have added here. So now we are executing a continuous scan, so motor does not stop, and we are able to see on the same online plot the result of the scan. So this already allowed us to reduce the time of the scan, but it was not very impressive. So in order to achieve better performance, we need to synchronize by hardware. So we define a synchronizer element in the system, and we will configure it in the experiment configuration. And this is as easy as changing the type of the synchronization from software to the newly created element. And with this, it is possible to execute the scan, now this time without the latency time. So this scan will proceed much faster, and we synchronize by hardware here. Okay, so this is the demo that I wanted to show you. And now I will proceed to the continuous scan application that will run at ALBA using exactly this software. So first is at the MSPD Beamline, we execute the powder diffraction experiment where we scan the outer circle of the diffractometer and acquire the diffraction pattern using the multi-crystal analyzer detector. We use the hardware synchronization for that, and this allows us to reduce the experiment time from 9 hours to 40 minutes. Another setup is at the class Beamline, where they execute absorption and emission spectroscopy experiments. So they scan the beam energy using a double crystal monochromator. And they acquire numerous experimental channels, up to 40 channels in the same experiment, which are the ionization chambers or the fluorescence detectors. They also use hardware synchronization in the time domain or the position domain, and they were able to reduce the experiment time from 1 hour to 3 minutes. At the Boreas Beamline, they have two end stations. On the first one, they execute the absorption spectroscopy and dichroism experiments. So this one also requires the changing of the beam energy, but in this case, the beam energy is changed with a monochromator, but at the same time, the insertion device energy must follow the change of the energy. And they acquire the data using the total electron yield, and they were able to reduce the experiment time from 1 hour and a half almost to 2 minutes, thanks to the continuous scan. Another end station at this beamline execute the reflectivity scans, which requires continuous scan of 3 motors, the sample motor, the detector motor, maintaining the specular angle, and also the magnet. And the detection is based on the photodiode. And in this case, currently they use just the software synchronization for this experiment, so the time reduction is not so impressive like in other experiments, so from 17 minutes to 7 minutes. And the last example is not executed at the beamline, but in the auxiliary laboratory at ALBA, where the magnetic measurement lab, where they scan the magnetic field map of the bending of the magnets or the insertion devices. So they use a 2-dimensional scan, and where the Z axis is scanned in a continuous way, and the detection is done with a whole probe sensors. Here they use hardware synchronization, and they were able to reduce the experiment time from 7 hours and a half to 4 minutes, thanks to the continuous scans. As a conclusion, currently Sardana provides user-friendly and transparent continuous scans, which allow to scan any movables, also the pseudo-movables or virtual movables. It allows to acquire the 0D or 1D experimental channels and synchronize the experiment by software or hardware. The basic requirements of ALBA beamlines are currently fulfilled, and we could see the experiment time reduction of a factor of 20 where the hardware synchronization was used. We plan to deploy this new version at other scanning setups at ALBA. Also, other synchrotrons in the collaboration are planning to evaluate it for their needs. But this is not the end of the story, so we plan further enhancements, like currently we lack support for the 2D experimental channels, and also we plan to introduce a generic interface for the nonlinear trajectories in the scan. I would like to thank other people that were involved in this project, beamline scientists at ALBA Electronics section at ALBA, and also experts from other institutes that participated with comments. Thank you very much.
We may have time for just one quick question. We are running out of time.
Thank you for interesting talk. Hardware synchronization obviously depends on type of motion controller and detector. How many are supported, and what involves to adding more?
Currently, we have developed the plugins for the timing card from National Instrument for the PMAC and also for the ICALEPCS controller. But the interface is prepared to handle other type of hardware as well.
Okay, thank you, Zbigniew.